In the last video we talked about Concrete 101 and why concrete is such a great construction material, but I didn't mention its greatest weakness. Hey, I'm Grady and this is Practical Engineering. On today's episode, we're continuing the series on concrete with a discussion of reinforcement. This video is sponsored by Skillshare. More on that later. To understand concrete's greatest weakness, first we need to know a little bit about mechanics of materials, which is the fancy way of saying how materials behave under stress. Stress in this case is not referring to anxiety or existential dread, but rather the internal forces of the material. There are three fundamental types of stress: compression, pushing together, tension, pulling apart, and shear, sliding along a line or plane. And not all materials can resist each type of stress equally. It turns out that concrete is very strong in compression and weak in tension. But you don't have to take my word for it. Here's a demonstration. These two concrete cylinders were cast from the exact same batch, and we'll see just how much load they can withstand before failure. First, the compressive test. Under compression, the cylinder broke at a load of about 1,000 pounds. That's 450 kilo. For concrete, that's pretty low because I included a lot of water in this mix. The reason is my rig to test tensile strength isn't quite as sophisticated. I cast some eye bolts into the sample and now I'm hanging it from the rafters in the shop. I filled up this bucket with gravel, but it wasn't quite enough weight to fail the sample, so I added another dumbbell to push it over the edge. The weight of this bucket was only about 80 pounds, or 36 kilos. That's less than 10% of the compressive strength. All this to say, you shouldn't make a rope out of concrete. In fact, without some way to fix this weakness to tensile stress, you shouldn't make any kind of structural member out of concrete, because rarely does a structural member experience just compression. In reality, almost all structures experience a mixture of stresses. That's no more apparent than in the classic beam. This particular classic beam is homemade by me out of pure concrete here in my garage. Applying a force on this beam causes internal stresses to develop, and here's what they look like. The top of the beam experiences compressive stress, and the bottom of the beam experiences tensile stress. You can probably guess where the failure is going to occur on this concrete beam, as I continue to increase the load. It happens almost instantly, but you can see that the crack forms on the bottom of the beam where tensile stress is highest and propagates upward until the beam fails. You see what I'm getting at here? Concrete on its own does not make a good structural material. There are just too many sources of tension that it can't resist by itself. So in most situations, we add reinforcement to improve its strength. Reinforcement within concrete creates a composite material, with the concrete providing strength against compressive stress, while the reinforcement provides strength against tensile stress. And the most common type of reinforcement used in concrete is deformed steel, more commonly known as rebar. I made a new beam with a couple of steel threaded rods cast into the lower portion of the concrete. These threads should act just like the deformed ridges in normal rebar to create some grip between the concrete and steel. Under the press, the first thing you notice is that this beam is much stronger than the previous one. We're already well above the force that failed the unreinforced sample. But the second thing you notice is that the failure happens a little bit slower. You can easily see the crack forming and propagating before the beam fails. This is actually a very important part of reinforcing concrete with steel. It changes the type of failure from a brittle mode, where there's no warning that anything is wrong, to a ductile mode, where you can see the cracks forming before a complete loss of strength. This gives you a chance to recognize a potential catastrophe and hopefully address it before it occurs. Rebar works great for most reinforcement situations. It's relatively cheap, well tested, and understood, but it does have a few disadvantages. One of the major ones being that it is a passive reinforcement. Steel lengthens with stress, so rebar can't start working to help resist tension until it's had a chance to stretch out. Often that means that concrete has to crack before the rebar can take up any of the tensile stress of the member. Cracking of concrete isn't necessarily bad. After all, we're only asking the concrete to resist compressive forces, which it can do just fine with cracks. But there are some cases where you want to avoid cracks, or the excessive deflection that can come from passive rebar. For those cases, you might consider going to an active reinforcement, also known as prestressed concrete. Pre-stressing means applying a stress to the reinforcement before the concrete is placed into service. One way to do this is to put tension on the steel reinforcement tendons as the concrete is cast. Once the concrete cures, the tension will remain inside, transferring a compressive stress to the concrete through friction with the reinforcement. Most concrete bridge beams are pre-stressed in this way. Check out all that reinforcement at the bottom of this beam. Another way to pre-stress reinforcement is called post-tensioning. In this method, the stress in the reinforcement is developed after the concrete is cured. For this next sample, I cast plastic sleeves into the concrete. The steel rods can slide smoothly in these sleeves. Once the beam cured, I tighten nuts onto the rods to tension them. Under the press, this beam wasn't any stronger than the conventionally reinforced beam, but it did take more pressure before the cracks formed. Also, this one wasn't quite as dramatic because instead of failing the actual steel rods, it was the threads on the nuts that failed first. I hope these demonstrations help show why reinforcement is necessary in most applications of concrete, to add tensile strength and to change the failure mode from brittle to ductile. Just like the last video, I'm just scratching the surface of a very complicated and detailed topic. Many engineers spend their entire careers studying and designing reinforced concrete structures. But I'm having some fun playing with concrete, and I hope you're finding it interesting. I'd love to continue this series on concrete, so if you have any questions on the topic, post them in the comments below. Maybe I can answer them in the next video. Thank you for watching, and let me know what you think. Thanks to Skillshare for sponsoring this video. Just about every step of producing a video for this channel is something I learned to do through online tutorials and videos, and we all know how varied the quality of that content can be. Skillshare allows you to learn new skills from experts in their fields, producing high-quality classes like this one from world-famous Burley graphic designer Aaron Draplin. I make a lot of technical illustrations on practical engineering to communicate complex topics, so learning new tips and tricks from someone like AJD is so valuable to me. If you're trying to learn a new skill or improve on an existing one, cut through the clutter of online tutorials and click on the link in the description below to start learning with Skillshare. The first 1,000 people to sign up will get their first 2 months free. Again, thank you for watching, and let me know what you think.